look at inverses of matrices, and then we're also going to look at how we can use the inverses then to solve systems of equations with matrices. Before I actually get into inverses, I'm going to talk about something called an identity matrix, because the identity matrix helps us figure out if two matrices are in fact inverses of one another. Okay? So an identity matrix is a square matrix, rows equals columns, and it has a diagonal of ones, and all other entries, maybe I should say other there, all other entries are zeros. So someone said first hour, hey, isn't that a lot like reduced row echelon form? Yes, it's very similar to reduced row echelon form. I would argue you could have reduced row echelon forms. Remember how we talked about, like, you could have a row of all zeros? Okay. We wouldn't have that in our identity matrix. So they are very similar in the way that they look, but not all reduced row echelon form is an identity matrix. Okay. Here's an example of a 2x2 identity matrix. 1, 0, 0, 1. See that diagonal of ones? Everything else is zeros. Here's an example of a 3x3 identity matrix. 1, 0, 0, 0, 1, 0, 0, 0, 1. See that diagonal of ones? Everything else is zeros. Okay, those are identity matrices. Now, why are they called identity matrices? Because if you multiply a matrix by that identity matrix, you get the same thing. No, it should be sort of like row echelon form. Yeah, I would think that if it was in the opposite direction, you might flip-flop, it might not be identity, like some of the terms. I'll practice that and see if that is actually true. But I would say the identity matrix is always going to be a diagonal of ones going down. Okay, so if you multiply any matrix by the identity matrix, you get itself. It's like multiplying a number by 1. You do 5 times 1, you still get 5. Okay, so you don't change the thing that you multiply by. Okay, so that gets us into an inverse matrix. Okay, an inverse matrix can be found. We're going to let A be an n by n matrix. If it's n by n, that would imply that our rows are equal to our columns, and so it is also a square matrix. First, I'm going to give you some notation, and then we'll talk, once you write it down, we'll talk about what that notation actually says. If A is an n by n square matrix, then we will know these two things to be true if it's an inverse. Okay, remember, because I'm using capital letters, I'm implying matrices here. Okay, so we're saying, let's take matrix A and multiply it by this here, which just means the inverse of A. We saw this with function notation. We had like F inverse. So maybe write down in your notes real quick, this is the inverse of A. If you multiply a matrix A by its inverse, then you get the matrix I sub n, which is just your identity matrix. So that's what we just talked about, the diagonal of ones and all the other entries are zeros. Okay. So how can you check if two matrices are inverses of each other? Do matrix multiplication. And David, what would I be looking for?
The identity matrix.
Yeah, if I get the identity matrix, then I know that they're inverses of each other. Now, if they're actually inverses, it is true reverse. And we talked about yesterday, like, if we multiply two matrices, is that commutative? A times B is equal to B times A? No. You would have saw that in number 47 on your homework. Part A, part B, you just switch your multiplication, but you don't get the same answer. So multiplication with matrices is not always commutative, but when you're working with inverses, you'll always get the identity matrix. As a side note, this sub n right here, that just means like whatever dimension square matrix based on the dimensions of A, or the order of A. Okay. So if you had a 2 by 2 matrix for A, you would get the 2 by 2 identity matrix. That's what I sub 2 would be. Okay, so let's prove that these two matrices here are in fact inverses of one another. Show that B is the inverse of A. Do what David said. David, what'd you say? Multiply my time. Now this is 2 by 2, so pretty quick and easy. I could probably do this one by hand. You certainly could plug these two matrices into your calculator and then do the matrix multiplication in your calculator to check to see that you get the identity matrix. I'm going to take the first row, 2, -1, times the first column, -1, 3. That'll give me -2 plus 3, 1. Take the first row, 2, -1, multiply it by the second column, -1, -2. 2 times -1 is -2. -1 times -2 is +2. 0. You see how that's working out? Bottom row, -3 times -1, 3. 1 times -3, -3. That's 0. -3 times -1 is +3. 1 times -2 is -2. 1. Did it check? Yeah. To prove that it's actually inverses, we should actually do it the other way as well. So we should do B times A. And you would run through the same system. Take a row in matrix B, multiply it by column in matrix A. So -1, -1 times 2, -3. That would be -2 plus 3, so I get 1. -1, -1 times -1, 1, the second column. That's +1 and -1 for a 0. Second row, -3, 2 times first column. -6 plus 6, 0. Second row times second column. +3 minus 2, 1. Are they inverses? Yes. Okay. So that's why we would talk about identity, because when you multiply by an inverse, you get the identity value. Christian?
Is it possible for AB to work out but not BA?
I would guess yes, because multiplication is not commutative. I don't know for certain. So I can add that to things that I will look at, along with the multiplying by the reverse diagonal. Good. Note that this is the same idea, like if you multiply real numbers by their inverses, you get the identity. So like a real number 3 has a multiplicative inverse that is its reciprocal. 3 times 1/3 is 1. That's how you know they're inverses, because they end up equaling that multiplicative identity value of 1. Okay, so the same thing is happening with the matrices. Okay, next up, find the inverse. Now, what I'm going to show you first is an algebraic method to find the inverse. I will sort of ruin the surprise for you and tell you this is not how I normally find the inverse of a 2 by 2 matrix, because on the next slide I'm going to give you a formula for finding the 2 by 2 matrix. But you know, where does one come up with a formula from some kind of algebraic proof? So this is not a proof but an example of why our formula on the next slide works. Okay? So I want to find the inverse of this 2 by 2 matrix, which if I don't know what the inverse is, I at least know it's also a 2 by 2 matrix, right? So this is like, let's say this is my matrix A, and then I'm going to multiply it by my inverse of A. What do I know is going to happen? We are going to use our calculators, but you know that there's an entire test that is no calculator. So bear with me. I would still like to teach you the mathematics behind the calculator and the formulas. That's what I'm doing right now. What should that product equal? The identity matrix. 1, 0, 0, 1. Okay, now we don't know what that other inverse matrix is, so I'm just going to fill it in with some variables. Okay. And for e's, I'm going to call them A, B, C, D. Okay. Now, do matrix multiplication. Okay, with A times A index. -1 times A plus -2 times C would be my first entry. 1A minus 2C. Pretty terrible. Okay. Next entry, I'm going to do my first row, second column. So I'm going to take 1, -2, and I'm going to multiply by my second column, BD. So 1 times B minus 2 times C. Now to get my second row entries, take my second row, -1, 3, multiply it by both of my columns. So for my first column, I would get -A plus 3C. For my second column, I will get -B plus 3D. Looks funny because it's variables, mathematical expressions, but that's what we would do, right? Okay. That is equal to the identity matrix that Catherine gave us. And what you have right now are two 2 by 2 matrices that are set equal to each other. We talked about matrix equality yesterday, and what we're saying in matrix equality is corresponding entries are equal. So what I can do is set up two systems of equations. Notice in this first column, I have only the variables A and C. The first row is equal to 1, the second row is equal to 0. So I could write those out. A minus 2C equals 1, -A plus 3C equals 0. Can you solve that system? Yeah. Okay, it's already set up for elimination quite nicely. I'm going to say solve the system. If I just stack and add right now, my A's will cancel. I'll get C equals 1. And if I know C equals 1, then I can find A. So I'm going to say by substitution, A minus 2 times 1 is equal to 1. A minus 2 equals 1. So A equals 3. So I just found A and C. Can I also find B and D? Yeah, same idea. Could you please solve for B and D real quick? Use the second column and its corresponding entries in the identity matrix to make your system. Solve that system for me for B and D. equals 1 by substitution. Plug that back in. B minus 2 times 1 equals 0. So B equals 2. So now we could say our inverse remember is this matrix right here. We're going to pull that over and we'll just sub in for A, B, C, and D. A was 3, B was 2, C is 1, and D is also 1. If I took that 2 by 2 matrix, multiplied it by the matrix I first gave you, we should get the identity matrix. It's not terrible, right, to solve algebraically? Okay. But because we're going to be using inverses quite a bit to solve for systems, we want a quicker method to do that. And you could imagine how, like, when I multiply by that A, B, C, D matrix, it's always going to be kind of the same system, right? So it's going to be somewhat similar. The numbers are going to change depending on matrix A, but the idea of solving the system remains the same. So here's how we can find the 2 by 2 matrix for any, or sorry, the inverse matrix for any 2 by 2 matrix without having to do the whole systems of equations. Now, I will say this. On your homework assignment, if it's 2 by 2, you should be going no calculator. If it's 3 by 3, so 2 by 2 would be a no calculator, and 3 by 3 would be use a calculator. Suppose A is a 2 by 2 matrix. This time I'm calling A instead of A inverse, A, B, C, D. If that is your original matrix, this is your inverse. A inverse is equal to 1 over AD minus BC multiplied by a 2 by 2 matrix where we rearrange some things. I'll let you write them down and then we'll kind of talk about them. I'd say we're halfway through. So you just have to make sure at some point you go back and get the other part. Okay, now you have this little scalar out front, this 1 over AD minus BC, okay? And that's just the difference of the products of the diagonals. So you do A times B and B times C, okay, in that first one. And we'll talk more about that next week. That has a special name. But over here, then you're multiplying it by a new matrix. Think very carefully so that this will be easy for you to do by hand and by memory. Think along the diagonals. So on that first diagonal in matrix A that has A and D going down, what do you do on that diagonal when you're finding the inverse? Swap them, right? D becomes A becomes D, flip-flop the numbers, okay, on that first diagonal. Okay, look at the other diagonal. Okay, the diagonal CB going up. What do you do to the entries there? Negate them. Don't swap them, only change their signs, right? So if they're positive, make them negative. If they're negative, make them positive, but leave them where they are. Okay, so you only do one thing to both diagonals. On the first diagonal, swap the entries. On the second diagonal, change their signs. Now, let me ask this question, and I will have you have a quick chat with your small groups. When would an inverse not exist for a matrix? What part of our matrix formula would tell us when an inverse does not exist? Think about that.
I literally said everything that she said half a second ahead.
There's only one right answer. And I expect most of the groups to be able to get it. Okay, share with me. How do you know there's no inverse? AD minus BC is 0. Did anybody else describe that differently? If AD is equal to BC, right? Because then when you subtract them, you would also get 0. Okay, so that would be great. If that happens, you would be doing 1 divided by 0, which is undefined, and then you're multiplying it by a matrix, so that means there is no answer. So, interestingly enough, not all square matrices have inverses. So you don't have to have an inverse. You'll only have an inverse if the product of your diagonals is not 0. Okay, or the difference of the product of the diagonals is not 0. Okay, good. Okay, let's find the inverse using the formula. See how quick and easy this could be. Here's an example. Matrix A is 5, 4 in the first row, 2, 1 in the second row. We'll go ahead and calculate the inverse there. Using my formula for A inverse, I'm going to do 1 over, and then you have to do the difference of the product of the diagonals in the correct order, otherwise you get a wrong sign for all your entries. So it's going to be 5 times 1 minus 4 times 2 or 2 times 4. It doesn't matter which way you do that. And then set up your work in that 2 by 2 matrix. So along the first diagonal, switch 1 and 5. Along the second diagonal, make them both negatives. Negative 2, negative 4. What do you get for your scalar out in front? 1 over negative 3. Okay, so you get negative 1/3 times all of this. And I would request, if I ask you to find the inverse, that you take that scalar and you multiply it through your actual matrix. So that all you have is a matrix, not a matrix and a scalar in front. So my final answer for the inverse of A would be something like negative 1/3, positive 4/3, positive 2/3, and negative 5/3. Is that okay that I have fractions there? Yes. Totally okay. Any questions? Okay. If you want to take some time later tonight, if you're really curious, you could go ahead and try to solve that matrix using our systems of equations, and of course you're going to get some fraction solutions, but you should come up with the same inverse that we did in that previous example. Okay. Last thing we want to talk about then. Oh no, second to last thing we want to talk about. Sorry. I forgot about the calculator work. If it's 3 by 3, this one won't take long. Do it in your calculator. Like, I'm not going to give you a formula for a 3 by 3 matrix. Okay, so do it in your calculator. So you would pull up your calculator.
Yeah, you do a matrix A and then a matrix B.
I'll grab my calculator here, pull it over. I did try this morning to post this like emulator that I'm using on my screen on my website, but I haven't had anybody try to download it onto their computer, so I don't know if it actually works. So if you don't have a graphing calculator at home and you want to go home tonight and try, go to my website and click on the 2 links for graphing calculator. One will give you this like skin for the graphing calculator. The other one is the operating system, which once you have this open, you have to go to File and then Open, and you open the operating system. Okay. So if you have time and you don't have a graphing calculator at home, you might try it and let me know if you can even download the things, because I don't know if that works or not. Okay, so I've already done all my work, but you're going to go into second inverse, and you can change one of the matrices that you've already used, or you can get a brand new one. I went into A. Oh, I always do that. Man. I went into Edit A, and I changed it to a 3 by 3, and then you can see in my first row 1, negative 2, negative 1, 0, negative 1, 2, and 1, negative 2, 0. Type all that in. So I'm typing in the problem that's on the screen in larger print. That's probably easier for you to see than the graphing calculator. Okay. Is everybody okay with getting into their matrices? Okay. Now, to do the inverse, you're going to have to quit that. So I do second mode. Okay. And then for my TI people, you want to find the inverse of matrix A, so you're going to go grab A. So you're going to do second inverse to get to the matrix menu. Under the names menu, pick the one that you just used. If you called yours C, then grab C. I'm going to grab A. Okay. And then remember, I'm always calling that when we go to the matrix menu, I'm calling x to the -1 the inverse. That's the button that you hit. So type the x to the -1 button without the second in front of it. If you do second, it will take you to matrix. If you just type that -1 button, that will get you to the inverse. And then hit enter, and it gives you your inverse matrix.
I do too.
And my Casio people, you got it? So then you can just write out your system, or not system, matrix. So you went in to get A, and then you did your inverse button, no seconds. Everybody okay with that? No? Yes, Joe, please help Jordan. My Casio people must rely on other Casio people. It is necessary. Okay, let's move on to our last one. For real. We're going to use an inverse matrix to solve the system of linear equations, which I have there. We're going to do this one because it's 2 variable. It'd be a 2 by 2 matrix, so we're doing it by hand, right? If that were a 3 variable system, then we would be doing it in our calculator. Okay, so in order to be able to solve a system using matrices and inverses, you're going to set up something, instead of an augmented matrix that we can turn into row echelon form, we're going to write something just called a matrix equation. Okay. And the matrix equation basically takes your coefficient matrix times your variable matrix, and then it equals your constant matrix. And so you actually write it out with 3 separate matrices. The coefficient matrix is from the system, it's the coefficients to all the variables. So this one's only 2 variables, it's a 2 by 2. Okay? So my coefficient matrix looks like 5, -3, -8, 5. I don't include the x and the y's because that's just coefficients. Okay. My variable matrix is a 2 by 1 with x and y in it. Think about last night's homework with matrix multiplication. If you were to multiply this 2 by 2 by the 2 by 1, you do 5 times x plus -3 times y. That's that first line. And then you would do -8 times x plus 5 times y. That's your second line. So by writing it out like that, we really have that same piece in the system. And then it's equal to a 2 by 1 that is your constant. Now when I'm introducing this topic, I like to think about it like, what if this was, back in Algebra 1, the equation 3x = 6? How would you solve? Do what? Divide by 3, which is really doing what? Dividing by 3 is the same as multiplying by 1/3, which I kind of talked about really quickly. These are inverses, right? So if you were to multiply both sides by the inverse of this coefficient matrix, then it will turn out to be the identity matrix, which will give you just x and y. And then you'll have multiplication on the other side that will be your solutions for x and y. So this is our coefficient. We're going to call it matrix A. We want to find the inverse of matrix A, our coefficient matrix. And again, this is why we would use our formula. It's a little bit quicker. We're going to do 1 over 25 minus 24, which is just 1. So that's going to be 1 over 1, which is super nice. 1 times, in matrix A, switch that first diagonal, which doesn't look any different, but change the signs of the second diagonal, so we'll get 8 and 3. And then that's really just this matrix, correct? 5, 3, 8, 5. Okay, that's my inverse matrix. And so we want to multiply both sides of the equation by the inverse. So on this left side where I have my original coefficient matrix, I could just put the inverse matrix right in front of it. Are you okay with me doing that? Okay. So I'm going to have my inverse matrix, which is 5, 3, 8, 5, times my coefficient matrix, 5, negative 3, negative 8, 5, times my variable matrix, x, y. I'm thinking this is my inverse times my matrix, this is my variable matrix, I'll just call this x. And then I have to be really careful on this side with my constant matrix, because this matrix is 2 by 1, and I'm going to multiply it with a 2 by 2 matrix. Where do I need to put the 2 by 2 matrix? In front or behind? So that I can multiply it. In front, so that the columns in the 2 by 2 matches the rows in the 2 by 1. Okay, so you have to always write your inverse first. 5, 3, 8, 5, followed by your constant. And that will always be true. Okay, so this is my inverse times my constant. Maybe I'll use C for constant, actually, because I don't want to confuse it with the variables. Okay, times my constant matrix. Okay, now on this side, we already know what should happen right here. Identity matrix. Over here, I would do my work. A 2 by 2 times a 2 by 1 is going to give me another 2 by 1. So I'll take the first row times the column. That'd be 5 times 7 plus 3 times negative 10. And then I'll take the second row times the first column. So that gets me the second row. 8 times 7 plus 5 times negative 10. And on this side, if you actually multiply the identity matrix by this variable matrix, you're just going to end up with xy. Right? 1 times x plus 0 times y is x. 0 times x plus 1 times y is y. Okay, so that is just what it is. And then on this side, you have 5 and 6. So I now know the ordered pair solution is 5, 6. So I did the 35 plus negative 30 to get 5, did the 56 plus negative 50 to get 6. Now, every equation is going to be just like that algebra equation. If it was 3x equals 6, you'd multiply by 1/3. If it was 5x equals 20, you'd multiply by 1/5. But you'd always multiply by the inverse. So the same will be true in your matrix equation. You'll just always find the inverse and multiply it in front of your constant matrix. Okay, and that should get you your solutions. If it's 3 by 3, use your calculator to find the inverse. And then you can choose to practice matrix multiplication or do the matrix multiplication itself. Your homework assignment is on your goal sheet. It's 10 problems. I appreciate when you do your homework assignment. I think it makes the questions more meaningful to everybody at the beginning of class. So please take the time or find the time tonight to do those 10 questions. Some of them will be very simple, like find the inverse. And then others will be those where you actually have to solve. Okay, and some will be calculator and some will be no calculator. If it's 2 by 2, no calculator. If it's 3 by 3, use a calculator.